All right. Hello, everyone, and welcome to week number 4 of Qubit by Qubit's Intro to Quantum Computing course. I hope you all had a restful and enjoyable week, and that you didn't struggle too much with the homework this week, although we will be going through a little bit of that before we start the rest of this lab. We do, as usual, have a pretty packed agenda, so I'm just going to jump right into things here. Today's lab will be on matrices and linear algebra. So we will introduce the concept of matrices, why we need them, why they're important, all that kind of stuff. And by linear algebra, we basically just mean talking a little bit more about various operations to do with vectors. So a quick overview of the lab today. We're going to start off with another just administrative announcement. Hopefully all of these announcements are coming at you from like a bunch of different angles. We're going to bring them up in labs. So if you don't see anything else, at least you should see these ones, just to keep you up to date with what's going on in the course. Then we will do our usual attendance quiz. And as usual, the quiz passcode is right there in the bottom right of the slide deck, just in case you do join late any point in the future. And then we'll do sort of the main part of the lab. We'll do the pre-lab Zoom feedback, questions from last week. Actually, a heads up, there are no predefined questions, I guess, from last week. The TA group, we were watching Piazza as we normally do, and couldn't really pick out any common themes of misunderstanding. So the questions from last week, this week, is just going to be me opening up the chat and asking you for any questions that you had from the homework. So it'll be a lot more free-flowing if you want to get some questions ready. Then we'll do the lab content on matrices and vectors, and then finally the post-lab Zoom feedback as usual. One more quick reminder that this lab is one that's recorded, and so I will be probably going overtime to cover the optional material, but I will make it very clear when the optional material is beginning, and you are more than welcome to sign off at that time. So the announcement is that we are starting up something called Student Assistant Virtual Office Hours. So the Student Assistant program, some of you might have heard of it because we put out applications for any students, such as yourselves, to apply. And we basically went through and interviewed a bunch of students who sort of had some previous experience with quantum computing or mathematics, and who are going through this course sort of to learn new technology toward the end of the course or just for a refresher. And we asked them to be student assistants. So they're kind of like another level of TAs, where every Friday from 8 a.m. till 8 p.m., they will be hosting office hours, which is essentially just a time for you to go to them, ask questions about homework, work through some practice problems, whatever you need if you really need just sort of some extra practice with a particular week's content. So as it says here, they're available to review lab and lecture materials, walk through homework problems, or answer any other content-related questions you might have at the end of each week. Importantly, the link to office hours is found under the course materials module on Canvas. So if you ever have trouble with one week's material, I would certainly encourage you to check out the Student Assistant office hours. All right, let's jump into the Canvas quiz. So by now, I think you should know the drill. The quiz should appear on Canvas under lab number 2A. So go ahead, sign into your browser, open that up. The quiz password for this week should be 7264. And the question you'll be asked is, again, not graded, but it is related to last week's content. So the question is to find the magnitude of the vector 1, 0. I'll give you the answer to this after everyone has 30 seconds or so to fill out the attendance quiz. As it says on the slide here, the quiz is not graded, but it does count for your attendance. So make sure you go ahead and fill it out. I will also open up the chat here. So if anybody has problems accessing Canvas or seeing this quiz, feel free to just message in the chat. If not though, I will give you 30 seconds or so to fill out the Canvas attendance quiz, and then we'll move on with the lab. Okay, so hopefully everyone's had a chance to fill in the Canvas attendance quiz. It looks like we didn't get any messages in chat, so I will take that as a positive sign that everything went okay. Hopefully that continues to work throughout the rest of the semester. Once again, though, if you do ever have any problems, feel free to post on Piazza, or I guess the more appropriate place would be to post in Discord for any of these sort of administrative questions. Okay, so now we're going to launch the pre-lab feedback. So same question as always, on a scale of 1 to 5, how comfortable do you feel with this week's material? So go ahead and use the Zoom poll for that. Let me know how you're feeling about matrices and the various vector operations that were introduced this week. So as the votes come in here, I think it looks pretty similar to last week, which is to say, not super confident, but that is okay. We are gonna take the time in this lab session for sure to, as usual, reintroduce things, go through some practice problems, and make sure that everyone feels grounded with this stuff. All right, thank you for filling out the poll. Okay, so this is the part I alluded to at the beginning, questions about the content from last week. Now, as I mentioned, we didn't have any sort of common threads that we noticed as far as questions. So I am more than happy to just take any questions that folks have here. Don't want to spend too long on this, but for sure, if we want to walk through a practice problem or two, we can do that. So if there were any questions from last week that seemed unclear or that you struggled with on the homework, feel free to throw them in the chat and we can take a look at them now. So I got one question on matrices. We are going to get to matrices later on in this lab, so I'm just going to leave that until then. Okay, yep, thank you for letting me know it's your first lab. I think the biggest thing to know is just make sure you filled out that attendance quiz at the beginning. Okay, so does anybody else have questions on last week's material? I'll give it struggle with the multiplication of matrix. Okay, so again, all of the stuff to do with matrices, we will go over later in this lab. And so maybe I'll just try and save a bit more time for that for sure. Number 15. Okay, let me just quickly pull that up. Oh, 1 plus I in polar form. Okay. Sure, yes, thank you. Yeah, so we can quickly go over that. So I'm assuming the question was just, given a complex number, 1 plus I, express it in polar form. So if you remember from last week, there's there's one slide that I showed that had it was toward the end of the lab, and it had a step-by-step sort of like summary of how to do this. And if I recall correctly anyway, the summary goes something like this. Number 1 is to find the modulus of the complex number. Number 2 is to find the angle of the complex number. And then number 3 is to write it in the form r times e to the I phi, remembering that by Euler's formula, this is equal to r times cos phi plus I sine phi. And remember, we talked about how this cos phi plus I sine phi thing is really just a point on the unit circle. And essentially, just by some magic, you're able to write that as an exponential. And last week, we talked a little bit about why that is really not intuitive. But it's something that we're just going to take for granted for now. So I'm going to follow through these steps. So first of all, we will find the modulus of this number. So remember, the modulus of a complex number is written just with single lines around it. So I would write this as the modulus of 1 plus I. And the modulus of, I'm just going to jump down here for a sec to write the more general form. The modulus of a complex number, we learned, was the square root of a squared plus b squared. So here, the real component a is 1. The imaginary component b is also just 1. Imagine there's a invisible coefficient 1 in front of the I there. And so to find the modulus, we're going to take the square root of 1 squared plus the coefficient in front of the I is 1 squared, which is just the square root of 2. Okay, and in this final formula in step 3, we call this thing r. So we found our r is square root of 2. Next up, we're going to find the angle. Now remember, the angle of a complex number is a very similar idea to finding the angle for polar coordinates. So we use this inverse tan formula. And the angle of a complex number, which we sometimes write like this, is just going to be the inverse tan of b divided by a. So this should look very similar to the polar coordinate translation. So again, our b is going to be 1 here. Our a is also 1. So this is just 1 divided by 1, which is inverse tan of 1 itself. And then if you work that out on a calculator, you should get that this is pi over 4. And it's okay if that was just a decimal number as well. Now in our final formula, we call this thing phi. So now we've found our radius r, we've found our angle phi. And so the last step is to write this as r e to the I phi, which is just going to be square root of 2 e to the I pi over 4. All right, so hopefully that helps a little bit. Let's see, somebody asked, can we go over multiplication of complex numbers, question 9. So I'm going to say for the time being, no, just for the sake of time. I know I'm being wary of the people who said earlier that they want to see stuff about matrices. So I think we'll just leave it at this question for now. But if you do have any other questions about last week's, definitely feel free to go ahead and post it on Piazza. Okay, so let's move on to this week's content. So as I alluded to before, we're going to be talking more about vectors and introducing matrices this time. So first of all, we're going to talk about some new operations with vectors. So we're going to talk about something called normalization and the very related concept of unit vectors. And if you're thinking, where have I heard the term unit before? It should remind you of something called the unit circle. And it turns out that these are very related concepts. Then we're going to do vector inner products, which is pretty much just a mathematical tool at this point. And then finally, we will do matrices, which is kind of the biggest topic for this week. And then just to make a note, again, this optional content, I will be going over it today because this lab is recorded, but I will let you know when you're free to leave because you're under no obligation to stay for the optional content. So before we jump into things, I wanted to take a bit of a step back and tie all of what we've been talking about with vectors, matrices, complex numbers, all that kind of stuff, try to tie it back to quantum computers. So at the very, very highest level, a quantum computer is basically this box that modifies qubits. So I might have, a whole bunch of qubits over here that are my input. They're going to pass through our quantum computer and they will be output again as qubits, but now those qubits are going to be modified in some way. So obviously this is very high level, but so far what we've been looking at is basically how to represent qubits with math, right? And how we do that is with vectors. So last time we talked about how qubits versus classical bits, hopefully this is all review. A classical bit could be either 0 or 1. A qubit could be a superposition of 0 and 1. And in fact, we wrote these things as ket 0 and ket 1 to signify that they are vectors. And then finally, we talked about the mathematical notions of scalars and vectors. So a scalar was just your average number that you are all familiar with. A vector is what happens when you put two numbers together. So another way of explaining this would be a scalar does not have a direction, a vector does have a direction. And that was one of the key points made in last week's lecture. Remember, we also talked about how there was another way of representing a vector. Obviously, you can put this little arrow over it and everyone's going to understand that you mean v is a vector. But another valid way to do it is to write it inside a ket symbol. And so this is why when we write qubits, we write them with kets. It's to indicate that it is a vector. So let's say that we had two vectors, u and v. We've gone ahead and drawn them on the Cartesian plane here. And we wanted to compare them. And so all I mean by comparison is basically the same thing that you would do with regular numbers. So if I asked you to compare the numbers, -3 and 2, for example, there's a couple of ways you could do this. You could say that -3 is less than 2. If you wanted to compare their absolute values, you could. So you could say if the absolute value, oops, sorry, I meant to say -3. The absolute value of -3 is in fact greater than the absolute value of 2. I mean, you could do a whole bunch of stuff, right? You can imagine that there's pretty much infinitely many ways to compare two different numbers. And so here we're just going to introduce a couple ways of comparing vectors, because this is sort of our new type of number. And the first idea that you might have is kind of like the -3 + 2 absolute value example, is to compare the lengths of the two vectors. So if we look at our picture over here, one thing that you might say to describe this is that u seems to be longer than v in some way, right? Excuse me. And so we want to try and express that mathematically. And the way we do that is with the magnitude of two vectors. So to go ahead and compute the magnitude, we've been through this before. I'm just going to do both of these fairly quickly. Remember, we use this double bar to denote the magnitude. So I'll do magnitude of u here. Then we'll go ahead and use the formula that's given there. It's just the square root of the squares of the two components, which is a bit of a mouthful, but all that means is you put the square root, and then we plug in 3, square it, and then we take the 2, square it. We get the square root of 9 + 4, which is √13. So that's the magnitude of u. And then the magnitude of u. Now we move on to the magnitude of v. Same idea, square root, but now we're using the components given up there in the vector v. So we get 2 squared + 1 squared. And that gives us √4 + 1, which is √5. So this is a mathematical way of saying that, yes, u appears to be longer than v. And that is a perfectly valid way of comparing two vectors. But you might be asking, you already knew this from last week, so why are we talking about magnitudes again? Well, partly just for review, but partly because it leads into the second idea. We know from polar coordinates that vectors are described with sort of polar representation of vectors. They're described with a length, which is what we just calculated, and an angle. So what if we wanted to compare the angles of two vectors? Well, it turns out that we can define something called unit vectors. And essentially what a unit vector does is it makes the lengths of the vector all equal to 1. So the lengths of the vectors will be equal after you turn them into unit vectors, and the only difference will be their angle. The way that you actually compute a unit vector is you take the vector itself, u with an arrow above it, you divide it by the magnitude, which is what we just saw in the previous slide. And then typically the way we denote a unit vector is with this little upward hat arrow thing. And it is actually called hat. So if you ever hear me say u hat or v hat, it is referring to this symbol on top of the u. And it basically means that we've taken our vector u and turned it into a unit vector. So I'm going to go ahead and do an example of this, turning u into a unit vector. So the unit vector of u is denoted as u, but instead of an arrow over top of it, I put a hat to say that it's a unit vector, which is really just a special type of vector. This is going to be equal to, as we said there, u with an arrow, that's our regular vector, divided by its magnitude. Okay. Now we just plug things in. So u is 3, 2. The magnitude of u from the previous slide was the square root of 13. And when you have a vector divided by something like this, you actually just divide each individual number by root 13. So this is equal to 3 over root 13 and 2 over root 13, just like that. And if you plug this into your calculator, you would get something like 0.832 and 0.555. So even though that divided by root 13 thing looks kind of ugly, at the end of the day, these are just two numbers. And when you put two numbers on top of each other, you just get a vector as usual. So what does this look like? Well, over here, we've drawn our vectors u and v just regularly on the Cartesian plane. If we go to their unit vectors, we are essentially scaling them. So we're dividing them by their length so that their new length is exactly equal to 1. So you might notice that both of these vectors now, they still have the same angle that they did before. Notice how the angle of those two arrows does not change. All that changes is their length. And so now we've made both of them sit on the unit circle. Okay. Why are they on the unit circle? Because now they have a length of 1 or a magnitude of 1. And that's why they're called unit vectors. Unit vectors have magnitude 1, they sit on the unit circle, which has radius 1. All of these ideas are connected. So when you hear someone say unit vector or u hat or anything like that, it just means take the same vector that I had, keep the angle the same, but make it sit on the unit circle by scaling it with some factor. So hopefully that is relatively straightforward. If not, though, we are going to have a question period soon. The term for this, so these individual vectors, u hat and v hat, these are called unit vectors, but you will also sometimes hear the term normalization used to describe this process. So the process of turning u arrow into u hat is called normalizing u. And so this whole process of making unit vectors is called normalization. All right, so let's do the other unit vector. We already figured out what u hat is, although if you want to take a second to do the math yourself again, you're more than welcome to. I'm going to launch a Zoom quiz for all of you to try and find out what the unit vector of v is. So just to clarify again, the problem is to compute v hat instead of v arrow. And remember, there's a difference there. I will quickly throw up the formulas that we had on the previous screen so you remember how to compute this. So I'll give you about 30 seconds here to start working through this question, and there will be a Zoom poll popping up any moment now for you to enter your answer of what v hat should be. So again, just use these formulas down in the lower left of the screen. We already computed the magnitude of v. It was just the square root of 5. And I just noticed there was one question in the chat. The hat character is specifying it's a unit vector. That is exactly correct, yes. So it's the same letter that sits under it, but if it has a hat on top of it, that means it's a unit vector. Okay, so it looks like we're still, a few people still haven't submitted their responses, so I'll give another 30 seconds or so. Okay, so as people are submitting their final answers here, I will really quickly walk through how to do this, but I already worked through how to do u hat. So if you do need a review, feel free to go back and watch that part of this lab. For v, we're going to use the formula down here. So v hat is equal to v arrow divided by the magnitude of v. Now, we already computed the magnitude of v. That was the square root of 5. You can work that out for yourself too if you'd like. Then we just plug in v up here, which is 2, 1. And then the final step is the sort of trick I said before, where dividing a vector by a number is the same as just dividing each individual element by the same number. So the answer you should have gotten was 2 over root 5, 1 over root 5. Okay, so let's keep going. Does anybody have questions about the content so far or about that last concept question? The chat should still be open, so feel free to throw your questions in there. Okay, so can you define magnitude? So briefly, magnitude was given by, I think we gave the formula back here. So this blue box here is the definition of magnitude. We have talked about it in a previous lab though. I think, oh gosh, I think it might have been the first lab. Someone can correct me in the chat if that's not true. But yeah, we did go over magnitude in a previous lecture. So if you're not sure how to do that, just go back and watch that. We'd go over it a little bit slower. So you can't simplify. You're more than welcome to simplify. If you want to work out sort of what the number divided by the square root is, you can just use a calculator for that. The vector points on the graph were wrong, really. Oh, yes, you're right. Yeah, good catch. So just to clarify, for you here, the X and Y coordinates were mixed up. It should be 3 as the X coordinate, 2 as the Y coordinate. V does look to be correct. That's just a graphical mistake there. Oh, the attendance quiz answer. Sorry about that. Yes, let me quickly pop back to that slide. Oh yeah, speaking of magnitude. So the magnitude of the vector 1, 0, if you work this out, it is going to be the square root of 1 squared plus 0 squared. Oops. 1 squared plus 0 squared, which is the square root of 1, which is just 1. The magnitude is basically the length. That is correct. You can rationalize the fractions. Yes, rationalizing the fractions is fine. Oh, sorry, I didn't realize that's what you meant by simplifying. But yes, you are perfectly welcome to rationalize the fractions. You don't have to, though. At the end of the day, everything is just going to get thrown into your calculator. Okay, so let's go ahead and move on. Next up, we're going to talk about the inner product of two vectors. So we start off with this equation in the blue, which frankly is really scary looking, right? So we have, it is scary looking, but I'm going to go over it in pieces. And so hopefully it makes sense then. I'm going to start off with just this term right here. So this is just how we draw inner product. The inner product of two vectors is written with these kind of angle brackets. And then you write the two vectors that you're taking the inner product of, and then angle brackets again. So this might look a little bit funny. I know that usually we're used to seeing stuff in math drawn with like a single symbol in between. So for example, addition is drawn like this. You wouldn't think to draw it in this way, but for whatever reason, this is how mathematicians choose to draw inner product. It just means inner product of V and W. Okay, next one. This is an equivalent way of drawing the inner product. So the inner product is actually defined as V, we call this thing dagger. So we would pronounce this V dagger times W. Now what the dagger is, it's called the conjugate transpose, which is again, a mouthful. And I think a theme in this lab, by the way, is that a lot of things are mouthfuls and kind of complicated at first glance. But once you work through some examples, they start to become easier. So V dagger is simply defined as V conjugate. So remember this little star thing. Actually, I believe we might have used bar to denote conjugate before. These are equivalent representations, but this is the same thing as just conjugate. And then we take the transpose of that. So taking the transpose just means turning a column into a row or turning a row into a column. So I'll show an example of that in just a moment. If you expand all of this out though, you get a sum that looks like this. And so we're basically taking the first element of V conjugated times the first element of W plus everything all the way up to the nth element. But for a lot of the stuff that we'll be doing in this course, we're only working in 2 dimensions. So there is a much simpler formula for this in 2 dimensions, which is just this. So V1 conjugate W1 plus V2 conjugate W2. That's really all you need to remember for this. So sure, we can look at this big fancy formula and we can try and understand it, absolutely. But for the time being, I'm gonna say the best thing to do is just to memorize this formula. Okay, let's look at an example of how to do this. Now, I will point out again, the same mistake with how this vector is drawn is here. So it should be right here, x coordinate is 3. Thank you again to whoever pointed that out. And we're asked to find the inner product of u and v. I'll throw the formula down on the bottom of the screen again, just so that we have it in our heads. And for these u and v, everything is real numbers. So remember, the conjugate of a real number doesn't change anything. So actually here, we can just kind of ignore the conjugate, and we can just use this formula, u1 v1 plus u2 v2. So remember, the way we write inner product is with these sort of angle brackets. So the inner product of u and v is what we're asked to find. And then we're just going to use this formula here. So what is u1? u1 is just the first element of the vector u, so that's 3. v1 is the first element of the vector v, so that's 2. Then we add on u2 times v2. So that's looking at the second element of u, second element of v. Just like that. And so one way you kind of remember the inner product, it's essentially taking the product of all of the rows between your 2 vectors and then adding them up. Maybe that helps, but if you prefer, you can always just remember this formula. It'll work. So this is going to be equal to 3 times 2 is 6 plus 2 is 8. And that's the answer. So the inner product of these 2 vectors is always going to be just a scalar. So not a vector, it's just a scalar. So let's go on and do another concept question. Again, this is just to make sure that everybody is getting practice with these kinds of questions. So this question asks us to find the inner product of u, which is the same as the previous slide. V has changed now. So watch that. Use these 2 definitions. The formula is again down here at the bottom of the screen. And so I will give you another minute or so to work out what the inner product of u and v is using that formula. And yes, you're absolutely correct. Both of the arrows here are wrong. Here, I can go ahead and draw the correct arrows just so that we're clear. My apologies for not catching that earlier, by the way. So the u vector should be right there at 3, 2. Then the v vector should be at -2, 3. So the x coordinate is -2, y coordinate is 3. It should be up here. Okay, so I'll throw up a concept quiz here, and you can throw your answer in the poll so I can get a sense of what everyone is doing. And let me see if there's any questions. Is this like the dot product? Yes, it is very similar to the dot product. There are some technical differences, so just follow the formulas that we're giving you here. But yeah, if you've learned the dot product before, it's very similar. Someone else asks, is it always scalar? Yes, it is always scalar. I guess just to be clear here, scalars are different from vectors, but it could be a complex number, which is technically a scalar. What does the inner product tell us? So that's something I'm not going to go into too much here. We are going to talk about it a little bit actually with this question exactly. But we're just going to see inner product a lot in quantum computing, especially later in the course. And so you will get a sense of some of the things it's used for there. All right, so as the last couple of people are filling in the survey, it seems like most people are getting this one. I'm just going to quickly go through what the math looks like then. We use the angle brackets to denote inner product. And then we use the formula down here. So again, we don't have any complex numbers, so we can ignore the little conjugate that's normally on the u's. And then we'll take the first row, product of those two, plus the second row, product of those two. And we'll find that this is -6 plus 6, which is 0. So this is one example of what the inner product tells you. If the inner product of two vectors is 0, that means that they are orthogonal, which just means that there's a right angle between them. So you might have already even seen that in the picture. But yeah, if you ever get an inner product of 0, that means that the two vectors make a right angle with each other. Okay, so hopefully the computation, at least, of inner product is clear, even if the interpretation is not so much yet. Does anybody have questions about inner product or how we did anything there? Okay, so someone asks, does order of operations matter? That is a really good question. So in the definition, we gave UV. Ooh, sorry, that's a really rough angle bracket. There we go. Okay. And we saw that it was U1 conjugate, I'll draw it with a bar here, V1 plus U2 conjugate V2. And so the order of operations here, just using like BEDMAS, is to put the brackets like this. So you do the multiplication first and then the addition. That is the way you have to do it. So don't try and put brackets anywhere else. Always do the multiplication first and then the addition second. Okay, so what does the inner product tell us? I'm not going to go into that right now, just for the sake of time, honestly. But if you are curious about that, we will talk about it later in the course. I can say that for sure. Or you can also post on Piazza if you want a faster answer. Okay, so how would you do it with complex numbers? Good question. So the formula stays the exact same for complex numbers. Let's suppose maybe my u has complex numbers, and so my u is 3 minus 2i and 1 plus I or something. And my v is 1 plus I, 1 minus I. Just as an example. So how would I do this? I use the exact same formula, but now the conjugate on the u terms matters. So remember, just a quick refresher, the way we do conjugate is we flip the sign right before the I term, okay? So U1 conjugate is gonna be this first term, 3 minus 2i, but instead of 3 minus 2i, it's the conjugate, so it's 3 plus 2i. V1 is not conjugated, so it's just 1 plus I. U2 conjugated again, so we have to take 1 minus I because it's the conjugate. And V2 is just 1 minus I, no conjugate involved. From here, you would go and use the content we covered on complex number multiplication. So remember, you have to kind of multiply things like this. If you saw my lab on that, you should recognize this. It's very similar to polynomial multiplication. It would take quite a while to work out, so I'm not going to do it here. But you would just write everything out, add them together. And in this case, you would probably get a complex number as your answer. Okay, cool. Thank you for the questions, everyone. Let's move on to the last topic, which is matrices. So this is the, I would say, one of the more important parts of the lab. We're going to take a step back to the high-level picture I talked about toward the beginning of what a quantum computer does. So as a quick refresher, we have our input qubits over here. They go into the quantum computer, stuff happens, and then they come out as output qubits. Now, we've talked a lot about qubits, really, because qubits are just vectors. They're drawn like this instead of like this. But in reality, qubits are just vectors. And so everything we've been talking about so far is kind of looking at how we use math, how we do math on the inputs, how we do math on the outputs. But what we haven't talked about yet is how we describe mathematically what goes on inside the quantum computer, right? What is this step in the middle? How do we get from one vector to another vector? And that is what matrices do. So if we draw it out on the Cartesian coordinate plane, we might have two vectors. We might have a vector called u1, which is the initial state. So this is sort of supposed to be like the input is u1, and then the output is u2. So imagine that this u vector represents a qubit, and after doing your quantum computation, you go from u1 up to u2. So it kind of moves your vector in the Cartesian coordinate plane. So if you think to sort of your intuition with transforming numbers, let's stop talking about vectors for just a second. If you had a number like 6 and you wanted to transform it to become its square, so for example here 6 squared is 36, how would you write this using math? Well, I think most of us would be familiar with the notation of using f of x equals x squared. And what this is telling us is that the input, which sits right there, equals the output, which sits right there. And the way we describe this transformation is with a function, f. Now, the same thing kind of is happening here with our vectors. We have u1, and it transforms somehow to become u2. And so you might think that it's reasonable to say f of u1 equals u2. And indeed, this is a very similar idea, and you could write it this way. But for vectors in particular, there is a more compact way of describing these types of transformations. And if you had guessed by now, it is the matrix. The matrix is sort of the way we describe certain types of vector transformations. So I've said matrix and matrices several times now. What actually are these things? Well, vectors, we know, are a stack of two numbers on top of each other. A matrix is a stack of two numbers on top of each other with multiple columns. So here we have a 2 by 2 matrix. Typically, we talk about the number of rows comes first. The number of columns comes second. Columns, there we go. So this S here is a 2 by 2 matrix. So how do matrices represent transformations? Here is super scary formula number 2 of today. I apologize for that. But this is what it looks like to use a matrix to represent a transformation. So again, let's take this sort of step by step and try and figure out what's going on. The first thing I will point out is the dimensions of everything involved here, because I know that there, or I heard anyway, that there was some confusion about dimensionality. So if we have an n by m matrix, so remember this means n rows, m columns. I can't spell columns today. Oh my goodness. Columns. And then we have a vector that is m by 1. So why do we write a vector this way? Well, remember, a vector is just a stack of numbers on top of each other. So what we really have here is m rows, right? However many entries you have in your vector, and only one column. So sometimes we might call a vector an m by 1 matrix. Okay, it's just because of the way that the dimensionality works out. So what happens when you multiply a matrix with a vector? Well, if you look at how this is drawn here, you might see the pattern. Basically what happens is the number of columns of the matrix has to equal the number of rows of the vector. See the two m's here. And when you multiply them, those two things kind of like cancel out, and you're left with n by 1 as your answer, which again is n columns, 1 row. So this formula up here, we're actually not going to use it in this lab because, again, kind of like before, everything we do here is only in 2 dimensions. And in 2 dimensions, the formula just looks like this. So again, we are starting off with a 2 by 2 matrix right here. And this vector, we can describe it as a 2 rows by just a single column. Okay, so I think the key thing to understand with dimensionality, honestly, is just row times column. If you can just remember the order of that and really ingrain it in your head, you will be okay. Okay, so this is the formula we use for multiplying a vector with a matrix. Let's go ahead and do a concrete example of this to see it in action. So suppose we're given a matrix that is 1, 2, 3, 4, and a vector that's 5, 6. What will this equal? Well, I put the formula at the bottom left as usual. You should notice the theme with this lab, by the way, is that everything is basically just, you have a formula that you kind of have to remember, but there is a trick to doing it. If you just do it enough, you can start to see the pattern. So for example, for inner product, you always take the product of the rows and add them up. There's a similar kind of idea here. But for now, I'm just going to use the formula. So I have a matrix, which is this thing, times a vector, which is this thing. And now I'm going to fill in just by the formula with what that thing should be. So A11 in this case is 1. X1 is the first element of our vector, 5, plus A12, look over here, that is the top right element, which is 2. And then we have the second element of our vector, 6. Okay, second row, we are now using A21, which is the bottom left of our matrix, 3. First element of our vector is 5, plus bottom right of the matrix is 4. Second element of the vector is 6. So again, that's just following the formula here. And one quick check that you can do for yourself is if you've done this correctly, the second number being multiplied should be the same. Okay, because notice here you have your x1s and your x2s, those should always match. So if you ever want to do a quick check for yourself, you can just look whether the columns of numbers being multiplied match. And then I'm just going to go ahead and carry out the multiplication. So we get 5 plus 12 and 15 plus 24. Then the last step is to carry out the addition. And so we get 17 and I believe 39 as the answer there. Okay, so now that we've got one example out of the way, let's go and do a concept quiz. So I'm again going to get a poll launched here for this question. And you're asked to find the result of multiplying the matrix 0, 1, 1, 0 with this vector, root 0.7, root 0.3. So again, I've put the formula down in the bottom left of the screen here. So just follow along with this formula. The most important thing here, honestly, is just patience, just to make sure you don't get your 1s and 2s confused. So just be sure that you follow that formula and you should get the correct answer. So I'll give about another 30 seconds or so. Actually, it seems like people are taking a bit longer on this, which is totally understandable. So I'll give a bit more time and then we'll go over the solution to this question. And actually, I will look at questions as well. Ooh, lots of questions, okay. Yeah, so is it a vector, still a vector if it's 3 tall? Yes, yeah, so a vector can be any number of elements stacked on top of each other. In this course, we're usually just gonna see them with 2 elements though. So then we asked, how would they cancel out? Yeah, good question. So actually 2 people asked about the dimensionalities. So I will go over that really quickly after we do this question. Actually, yeah, I'll save this until we get to the question slide. just so we can sort of finish the bit on matrix multiplication. Okay, so it looks like most people are starting to, actually, most people have finished the quiz. So I'm going to start going through it myself here. Again, we're just going to apply that formula in the bottom of the screen. So what do we get? Well, we get, I'm going to do this one a little bit faster. So this one is going to be 0 times root 0.7 plus 1 times root 0.3. Okay, so you should have gotten something like that. And then if you carry out the computation, the multiplication here is really easy because everything's just times 0 and times 1. And you should get that the answer is root 0.3, root 0.7. So if you look at this, you might have noticed that basically what happened is the two elements in our input vector flipped around in our output vector. So we just swapped the 0.7 and the 0.3. Now, if you have a good memory, this might remind you of something that we have seen before. Sorry, there's the answer. It might remind you of the X gate or the NOT gate. So no worries if this was not obvious at first. This is the first time we're sort of starting to introduce this idea. But in quantum computing, matrices are going to represent gates. And so if you remember, the definition of X was to essentially, if you had something times 0 plus something times 1, it would swap them to become, sorry, beta times 0 plus alpha times 1. And that's exactly what we see here. The top element and the bottom element have just switched around. And so this matrix here, this 0, 1, 1, 0 thing, is the matrix form of the X operator. Okay, let's do another example here. So for this one, we have a bit of a different matrix. By the way, here we have a coefficient on the outside. Much like before when we divided a vector by, you remember the modulus, sorry, the magnitude of V. The way that this works is you just write it as each of the elements divided by that number individually. So here it would be equal to 1 over root 2, 1 over root 2, 1 over root 2, and minus 1 over root 2 is sort of the full way of expressing that matrix. Equals something. And sorry, I'll wrap up this concept quiz here. And so for this kind of question, we use the exact same formula. The same formula that's in the bottom left of the screen here. So I will go ahead and fill out what this looks like. Again, starting off with the first row, we have A11, which is the first element of our matrix, 1 over root 2, times x1, which is just 0, plus A12 is the top right. So we have 1 over root 2, times the second element of our vector is 1. So far, so good. Down here, A21 is the lower left element, so that's 1 over root 2, times the first element is 0, plus minus 1 over root 2, times the second element is 1. Now, if you go ahead and work all of that out, you should get 1 over root 2 and minus 1 over root 2. Okay, so I'm going to go to the next slide just to confirm this answer. And indeed, that is what we got. And again, if you look at what this has done, again, only if you have a very good memory from a previous lecture, you might notice that this is what we called the Hadamard gate, what we represented with H. And so this was the gate that effectively created a superposition from a qubit. Now, again, it is entirely not necessary for you to memorize this right now. This is just sort of to start giving you a sense of how all of this connects back to quantum computing. To give a quick summary, we talked a lot in last week and this week's labs about vectors. Vectors are essentially how you represent qubits. Matrices, which we introduced this week, are how you represent quantum gates, which is essentially, remember that picture that had the input qubits and the output qubits? The gates are what goes on inside the quantum computer. And when you use a gate or operate a gate or apply a gate, you'll hear a lot of different ways of saying this, but it all means the same thing. Operating a quantum gate on a qubit is multiplying the matrix with the vector. And so we just walked through a couple examples of that. So we've gotten to our final question slide. So I will go back and look at some of the questions that were being asked. I think the biggest question seemed to be dimensionality. So let me just confirm that, because I did sort of glance over one detail. So if I have a matrix that is 2 by 2, for example, I'm not going to write an explicit example. Actually, I guess I can. We'll do the 1, 2, 3, 4 example. Sometimes, by the way, you'll see people write the dimensions as sort of a subscript under the matrix, just to sort of keep themselves clear on all the dimensions that are going on. So the way that you would multiply these out is you look at these two numbers here. They have to be the same, which they are here. If they're not the same, you cannot multiply those two things. Okay, so you've done something wrong if those two numbers are not the same. And when you multiply these together, these two numbers disappear, and we get back to a 2 by 1 as the result. Now, some of you might notice this is not exactly the result we had. So I think, what was the answer here? 1739. I wrote it like this. A more accurate way to write that would be like this. Okay, so, oh, actually, I'm sorry, that was correct. 1739 was correct. See, I'm getting myself confused here with all the dimensionality stuff. So yeah, sorry, this is entirely fine. When we get back to this matrix here, it has 2 rows and just 1 column, which is exactly what you would expect from sort of doing this canceling out of those middle 2 dimensions and ending up with 2 by 1 as your result. Yeah, my apologies there. All this stuff with dimensions can absolutely get confusing. So you just got to be diligent with all your numbers. Okay, so I'll go through, let's see, questions. I think the H gate is a matrix. Yes, you are correct. So the H gate matrix is exactly this. This is the matrix for the H gate. And we will see that again in the future, but this is just sort of a preview of that, essentially. All the gates are represented by matrices. Yes, you are correct. Okay, does the order in which you multiply matter? Yes, it does. So you always want to be multiplying the matrix first and the vector second. Writing it the other way around would not be correct. Slide 31, briefly again, sure. Or wait, slide 31 is the question. Oh, okay, yeah. So the H gate makes a 50-50 superposition. Exactly, yes. All right, so I think let's wrap it up there. I'm gonna go ahead and put up the post-lab feedback form just to see how people's understandings have changed. I think as a general sort of summary with all of this though, the concepts with matrix multiplication, vector inner product, all that kind of stuff, can certainly seem daunting at first because it's a lot of new words, a lot about, oh, sorry, I said slide about operating quantum gates. Sorry, I just want to put this up so that you have it. Oh, here we go. Yeah. Yeah, so what was I saying? With all of this stuff, with matrices and vectors, it's a lot of new terminology. It is a lot of new math. And we haven't really been able to explain to you yet why a lot of this matters. So hopefully matrix multiplication makes some sense because doing that multiplication is how quantum computing works. But some of the other stuff might not seem all that relevant yet. I promise it will matter, especially inner product. So if you're going to review anything, matrix multiplication and inner product are sort of the most important concepts here. At the end of the day though, all of these things are just simple formulas. So as you're learning it, I would definitely recommend just memorize the formulas so that you can do the questions that you're asked. The more sort of intuitive understanding will come with time. And really the best way to do that is just practice. Yeah, someone just said in the chat, confused on inner products. Why do we do it? Fantastic question. The best answer I think I can give you right now is that example on the right angle between two vectors. So if you ever wanted to find out if two vectors are at a right angle from each other, you would use inner product and see if it's zero. But what a non-zero inner product means is something that we will come to a bit later in the course. Okay, so thank you everyone for submitting the post-lab feedback. I'm glad to see I seem to have helped a little bit. We are going to launch into the optional content now. So as a final reminder to everyone here, please make sure you submitted your attendance quiz. The code is in the lower right of the screen there if you did not or if you forgot. So please be sure to do that. We are going to go on to the optional content now, which is multiplying matrices by matrices and inverting matrices. So you are welcome to stick around for that if you want, but if not, you're welcome to sign off as well. All this stuff is going to be recorded. Someone asked, is the optional content important? Eventually it will be, but for right now, it's optional because you don't need it for the homework. We aren't going to expect you to know it in the future. So if you need to sign off, go for it. No hard feelings. Really just stick around if you are particularly curious about some of these topics. So I'll give everyone just a couple of seconds or so to sign off, and then we will launch into the optional content for this week. Have a good night, everyone. Okay, so let's keep going with the optional content. So as I said in the, there we go. As I said in the very beginning, the two pieces of optional content this week, the first one is matrix multiplication. The second one is going to be inverting matrices. So these follow kind of the same theme where there's going to be a lot of weird looking equations. And the answer to how to do these things is going to be basically just memorize them. But we are going to talk a little bit about why these operations would actually be useful. So first of all, I'm going to go back to a slide that we had before. At least we had these first three items. Recall that the sort of mathematical way of representing a qubit is a vector. The mathematical way of representing a gate is a matrix. And so vice versa, every gate can be represented by a matrix. Every qubit is represented by a vector. And operating a quantum gate on a qubit is the same as multiplying the matrix with the vector. But we're adding a fourth point now, which is asking what happens if you operate multiple gates on a qubit, right? The ones we saw so far was just what if you had X or what if you had H operating on the qubit? What if you had both of them operating on the qubit? Then what happens? And the answer there is matrix multiplication. And that's what we're going to talk about first. So this definitely takes the cake for the most scary looking equation of the entire lab. Now, once again, I will say the only thing you really have to know is the two-dimensional version, which is down here. And that already looks kind of confusing. So we are going to do an example of it in just a moment. But before we do that, let's just make a quick mention of dimensionality again. Now we have an n by m matrix, which is the same as we had before. But instead of an m by 1, which represents a vector, now we have another matrix, right? So it could be m times k other columns. The same rule applies though, which is that the two numbers in the middle here have to be the same. So here they're both equal to m. When you multiply the matrices, these numbers kind of cancel out and you end up with something that is n by k. So n rows, k columns. Now with 2 by 2 matrices, that doesn't really make much of a difference because a 2 by 2 matrix, right? If all of these numbers are just 2, then obviously you're going to get as your result a 2 by 2 matrix. And so we're going to see that in an example. Before we do that though, I do want to talk a little bit about how you would multiply generally two matrices that are not 2 by 2. So I'm going to go through this a little bit quickly, just because it's not the most necessary thing to know right now. But it is just to give you an idea that there is a way of thinking about this besides memorizing this massive formula. The way that you multiply two matrices is you start off with rows in the first matrix and columns in the second matrix. So here I've highlighted the first row of the first matrix, the first column of the second matrix, and then you multiply each of these row and the column together. And all I mean by that is you take the first element here, the first element here, multiply them together, add it to the first element here, or sorry, the second element and the second element multiplied, and then you just keep doing that. So I wish I could actually show you with my fingers how I'm doing that, but basically with your fingers, you can follow along and you can point at the first elements here, multiply them together, and then you shift one of your fingers down one and the other finger right one, multiply those two together, add them, and then shift one finger right, one finger down, one finger right, one finger down, and keep doing that for the entire row and column. Then that will give you the first element of your resulting matrix. So you still have all of the other elements to do, but now you've done the first one. Notice when I did the first row and the first column, that gave me the element in the first row and first column of my resulting matrix. Now you just continue. So we move on to the second column of the second matrix, still just using the first row of the first matrix. You do the same trick. So you have your fingers pointed here, and then you move one of your fingers to the right, one of your fingers down, multiply them together, add them, multiply them together. And by doing that, you get the element in the first row and second column of your resulting matrix. And so on and so on. So you would do that for all of the different columns. Once you've finished all of the different columns, now you move to the second row of your first matrix. And you do the whole thing over again, starting with the first column, get that element, second column, get that element, and so on and so on. So multiplying matrices is a really tedious process. I might have bored a few of you just saying that. But the basic idea is fairly straightforward, where you have rows, columns, and you just need to do a lot of practice with it. Again, though, that's not really the most important thing, because you can always just memorize that formula at the bottom of the screen, and you can use it for 2 by 2 matrices in this course. All right, let's do an example. So this is only 2 by 2, so it won't take that long. First thing I'm going to do is I'm going to do the trick I said before, where we put this multiplier inside of the other matrix here. So this matrix stays the same. The second matrix, though, is actually 1 over root 2, 1 over root 2, which you should recognize as the H gate. We saw it before. And the first matrix here is actually just the X gate. So let's go ahead and apply this mega formula that we have here down on the bottom of the screen. Again, this is all just plugging in numbers. You have to keep track of your ones and twos, just to try and make sure that everything looks good. So A11 is the top left of my first matrix, that's 0. B11 is the top left of my second matrix, that's 1 over root 2, plus A12 is the top right of my first matrix, 1. B21 is the bottom left of my second matrix, 1 over root 2. So far, so good. So that's the top left of our answer. Now we do the same thing for the top right, bottom left, and bottom right. So just for the sake of time, I'm going to go through that a little bit faster, but it is just following these formulas. And yes, it is tedious. Yes, it is error prone, but really the best way to do this is just by practicing. So what do we get for the other ones? Here we're going to get 0 times 1 over root 2 plus 1 times minus 1 over root 2. Running out of space. Here we're going to get 1 times 1 over root 2 plus 0 times 1 over root 2. Here we have 1 times 1 over root 2 plus 0 times minus 1 over root 2. Okay. And then we just have to carry through all of the computations here. So in the first one, I get 1 over root 2. Second one, I get minus 1 over root 2. Oops. Just like that. And then down here, I get 1 over root 2 again. And here I get 1 over root 2 again. And so that should be our answer. I'm going to jump to the next slide. And indeed, that is what we got. So here they've just factored out the 1 over root 2. But remember, we can write this equivalently as 1 over root 2 minus 1 over root 2, 1 over root 2, 1 over root 2, which is what we got before. So tedious, yes, but all you need is that formula. All right, why do we care about matrix multiplication? Well, we started off with, remember, this was the Hadamard gate, H. This was the bit flip gate, X. And so you might guess that the circuit this represents is a Hadamard gate followed by an X gate. So you might notice that the sort of order of things was flipped around, right? Back here we had an X, then an H. Here we have an H, then an X. That is something to be careful of. People get confused with this a lot. When you're multiplying matrices, the order is reversed from how you draw it in a quantum circuit diagram, which is just kind of a confusing piece that you have to memorize. But yeah, this matrix that we have calculated here, this X times H matrix, is equal to this quantum circuit. And so any quantum circuit, any combination of gates is still just a matrix. It's just that you have to do this matrix multiplication to figure out what it should be. So as an example, if we started with an input qubit that was 0, 1, and we ran it through this whole thing, we would get an output qubit that looks like this. And you could do this by first figuring out what the H gate does. So that would be something like this, equals something. I won't do it right now. You can do this on your own for practice if you want. And then to pass it through the X gate, you would do the X matrix times whatever you just got. And then that would equal this result. But the faster way of doing it is to just take your starting state, 0, 1, and multiply it by the matrix we just found, this matrix multiplication thing, times 0, 1, and you would get the same answer. All right, second optional topic is matrix inversion. So we've talked about, well, let's do a quick recap again. We've talked about how to mathematically represent qubits. We've talked about how to mathematically represent gates. We've talked about how to mathematically represent applying a gate to a qubit. And then we just talked about how to mathematically represent multiple gates in a row. Here, we're going to talk about another kind of problem. That is, what if I give you the output, but not the input? So remember, if you knew the input, you could compute the output because you would just write H times the input vector, whatever it is, and that would give you this output, 1 over root 2 minus 1 over root 2. But what if you don't know what the input is? What if you know the output and you want to find what the input should be? That's where matrix inversion comes in. So here's the example I just wrote. You know that applying the Hadamard gate to some qubit is going to give you that result. You just don't know what that qubit is. So here's the way that I wrote it before. H times some vector is equal to some vector y. We know what y is. And if you look at this as a regular math equation, you might think there is an easy way to do this, right? You divide both sides by h. this is how you would do it with sort of regular numbers, right? You divide both sides by h, and then you find out what the question mark should be. Now, in matrices and vectors in linear algebra, we don't tend to write it this way, although it is a very similar idea. Y divided by h can also be written as h inverse. So remember, when you raise something to the power of -1, it just means 1 over that thing. So another way of writing it is just this. And indeed, that is how we write it in linear algebra. We say that the question mark is equal to h raised to the power of -1. And the way we say this is h inverse, or the inverse of h, times y. Then this whole thing here is just matrix vector multiplication, which we did earlier in the lab. So the only question is, how do we figure out what this inverse is? Well, it turns out that we have a formula for that, just like everything else we saw before. And again, I'm not going to go into too much detail about how we get this formula or how you sort of have some intuition about this formula. But all I'm going to say is you should memorize what it looks like and apply it. So if x equals a, b, c, d, then the inverse of x is this thing. Okay, so I'll wait here a sec just to let you absorb that, but you absolutely do not have to memorize this. It's just a formula. You can always look it up, and we're going to do an example of it with the formula at the top of our screen as usual to see how you would actually apply this in practice. So let's go ahead and work it out. Just using the formula here, x is our matrix, and so I'm actually just going to write this with the 1 over root 2 inside. So we have 1 over root 2, 1 over root 2, 2 minus 1 over root 2, as usual. And if we look at how x is defined, this thing up here is a, this thing up here is b, this thing down here is c, and our bottom right is d. So now it's just a matter of plugging things into our formula. We're going to go ahead and write 1 over AD minus BC. So that is going to be A is 1 over root 2, D is minus 1 over root 2, minus B is 1 over root 2. Oops, sorry. 1 over root 2, and C is 1 over root 2. So that's one big fraction. And then in our matrix, we have D, which is minus 1 over root 2, minus B, which is minus 1 over root 2, minus C, which is minus 1 over root 2, and A, which is just 1 over root 2. Okay, so if we work this out, here we're going to get minus 1 over 2, minus 1 over 2 again, so that's just minus 1. 1 over minus 1 is just going to be minus 1 times our matrix. And so what that ends up doing is just removing all the negative signs. So we end up with 1 over root 2, 1 over root 2, 1 over root 2, minus 1 over root 2. That is the answer that we're looking for. So my work is a little bit scrappy here, so I'll go to the next slide, which has it written out all nicely. And so we find that the inverse of h is 1 over root 2, 1, 1, 1, minus 1, which you might notice is the exact same as h itself. So we just went through all of this work to find out that h inverse is actually equal to h. It turns out, well, number one, this is not true for all matrices. There are certainly most matrices, the inverse is going to be different. But for a lot of quantum gates, this is the case. So as an exercise, if you want to try it for the NOT gate, or the bit flip gate, you should find that x inverse is also equal to 0, 1, 1, 0. So it's the same idea where the inverse is actually the same thing. This happens a lot for quantum gates. So just to do a recap of what matrix inversion was even for, we started with a problem where we knew what the output was, but we wanted to find the input. And so the way we solved for that was to do matrix multiplication with this thing called the inverse. So we plug in the inverse as a matrix, we plug in what our output should be, and then we can go ahead and solve for the question mark, which in this case is just 0, 1. Okay, so I will pause here for any quick questions, although of course with optional content, you don't really need to fully understand it. It's more just for your own curiosity. So feel free to throw out any questions. Otherwise though, the lab is done. That was all the optional content. As usual, this will be posted because it's recorded. So feel free to watch it again if anything didn't make sense. I will stick around for a little bit to answer questions on the optional material. But to everyone else, have a good night and good luck with this week's homework. So does anybody have questions about matrix multiplication or matrix inverse? How would you do matrix inverse for multiple gates? Good question. So if I had, like I had before, the X followed by an H gate, something like this, remember that the way we figure out what this is as a matrix is to do matrix multiplication. The only trick is that we have to reverse things. So this would actually turn into the matrix for H times the matrix for X, right? So then you would go through and do all the matrix multiplication stuff, use that big formula. You would end up with something, I'll just call it A. And then you would apply the inverse formula to A. So the inverse formula only works if you have one matrix. And so whenever you have multiple matrices, you have to first multiply them together using matrix multiplication and then use matrix inversion. I know that was a really fast answer, but I hope that made sense. Why reverse the matrices? Yeah, this is a good question. The short answer is that the way we draw a diagram like this, we sort of assume that time is flowing from left to right, right? So we start off with 0, then we apply X, then we apply H, and then we end up with whatever our output is, right? In matrix multiplication, if I have a state 0, the first thing I multiply it by should be X, right? Because that's the first gate I'm applying in this sequence. Then after I apply the X, I'm going to apply H to whatever the result was. And so if you write this out, it has the effect of essentially reversing what you saw in the circuit. Okay, so we'll do one more question here from Kubera about, is this equation true? I'm assuming that you're typing an equation. A by A inverse equals 1. Yes, exactly. So if you had a matrix A, for example, and you multiply it by its inverse, you do get the equivalent of 1. So in matrices, 1 is just a matrix that has all 1s sort of down the diagonal. And so you do always get that when you multiply by the inverse. It's very similar to how when you have sort of the inverse of two numbers, right? X times X inverse would be equal to X over X, which is just equal to 1, unless X is 0, but that's kind of an edge case that we won't talk about. All right, so I think we'll wrap things up there. Thank you everyone here for sticking around for the optional content. If you do want to watch any of this again, once again, the whole thing is recorded, so keep an eye out for it on Canvas. Good luck with this week's homework, and we will see you again for next week's lab.